Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in this lecture, I will be talking about design of packet tower for absorption for concentrated mixtures. Okay. So before we look at this concentrated mixture problem, maybe we can review the results we obtained for dilute mixtures and then see how they are different from concentrated mixtures. Okay. So for dilute mixtures, we found that the height of the packed column Z is given in terms of overall height transfer unit and then overall number of transfer units, where this HTOG is defined as G by KYA and NTOG is defined as integral y2 to y1 dy by y minus y star. Okay. Now, what I am going to show now is when we do for concentrated mixtures, we will have results of this form, that the height of the packed column can be given in terms of the HTG and NTG. Okay. You can see this letter O is missing here. That is because in this problem we used the overall mass transfer coefficient, whereas in the concentrated mixture we are going to use local mass transfer coefficient, meaning this HTG will be defined as G by FGA, where FG is the local gas phase mass transfer coefficient. Okay. So, you can see the difference between this expression and this expression. This involves the overall heat transfer coefficient, this involves overall mass transfer coefficient, and this involves local mass transfer coefficient. This NTG is defined as y2 to y1 dy y minus yi plus 1 by 2 ln of 1 minus y2 by 1 minus y1. So, you can see the difference between the NTOG for dilute mixture and NTG for concentrated mixture, they are slightly different. Okay. In which way they are different? Well, in the case of dilute mixture, we use the driving force with respect to the equilibrium concentration, which is y star, whereas in the concentrated mixture we will be using the interfacial concentration itself, okay, with respect to the local coefficient. So, if I have to show this diameter graphically, suppose if this is some y, in the dilute mixture we used this y minus y star as the driving force, okay, whereas in the concentrated mixture we are going to use the interfacial concentration. So, this is the driving force line. This slope will depend on the ratios of the mass transfer coefficients. We are going to use this yi, okay. So, this concentration difference is used for mass transfer of concentrated mixture, whereas this overall driving force is used in the dilute mixture. So that's the difference between using yi here versus y star here. Okay. In addition, we also have an extra term which goes as 1 by 2 ln of 1 minus y2 by 1 minus y1. So, okay, this is a constant term that depends only on the inlet and outlet concentration of the solute in the gas phase. So, the context of today's lecture would be to derive these set of equations and show that for the concentrated mixture based on the gas phase mass transfer. So, we should be able to show this. All right, okay, so we will get to it. So, the purpose of this lecture is to demonstrate these set of equations for the design of absorption column in a packed bed for concentrated mixtures. Okay. So, so the starting point for us is the writing the shell balance over a small thin shell of the column. We had shown before that the differential of gy by dz is equal to minus na and a. Okay. You can see that we derived this equation based on the shell balance or absorption column. Okay. So, here this a is the interfacial area per unit volume of the packing. Okay, this is a characteristic of the packing material. Na is the mass transfer flux, and G is the in the units of moles per unit area per unit time. Okay, so this is a molar flux. So, this is where we gonna make a kind of diversion when we apply this formula for the concentrated mixtures. In the case of dilute mixture, what we did was we took this G out because we said G will be constant, and then we went ahead. But here in the concentrated mixture, the amount of mass transfer from the gas to liquid is quite significant, that this G will not be constant throughout the column. So, G can be a function of the column height. Okay, so we cannot take it out. So, we have to deal with this variation of the gas flow rate G as a function of Z. Okay, so that's the thing. So, what we can do is we may recollect that we wrote the solute free molar flow rate Gs as G times 1 minus Y, right. So, now Gs is constant, whether it is a dilute mixture or a concentrated mixture. The solute free molar flow rate, the carrier gas, that flow rate is constant. Okay. For example, if I have to give an example, let us say you have CO2 air mixture. G is the total flow rate of CO2 plus air. Gs on the other hand is the molar flow rate of only the air, and since air is not diffusing to the liquid, we can treat the molar flow rate of air as constant. That means Gs, which I designate here as a solute free basis, will be constant. So, instead of working with G, we can work with Gs, and I know how to relate Gs and G because I know the composition. Okay, is it clear? We have done this before. If I know the mole fraction of the solute, 1 minus of that would be the mole fraction of the non-solute or the solvent here. Okay, so in this equation, both G and Y are changing. And now I can write G in terms of Gs, and so that I can actually make single variable here. Okay, Y will be the single variable here. So, I can substitute for G as Gs over 1 minus Y, and I can substitute that in this equation, right. So, I will get Gs So, now I can take Gs out because Gs is constant. and it's easy to differentiate this particular function. So d of y by 1 minus y will be 1 minus y whole square 1 minus y dy minus dy. So you will get 1 dy minus y dy and plus y dy over 1 minus y whole squared, and these two terms cancel. So you will get dy by 1 minus y whole squared. Okay. So now I can substitute that here. So I will have gs dy by 1 minus y whole squared is equal to minus NAA dz. So now I have only one variable here, and one more thing we can do is we can substitute back again this formula that gs by 1 minus y equal to g. So using this again, I can actually write g times gy by 1 minus y, right. So here I have 1 minus y whole square. So I can take 1 minus y 1 of that. So I can write gs by 1 minus y, and that is nothing but g. So I can now write g times dy by 1 minus y. On the right hand side I have minus NAA dz. So what I have done, I have written g in terms of gs, dealt with the differential, and I am actually reusing again the value of g, but now the g is outside the differential now, right. Okay, so then the next task is to write the expression for Na. So mass transfer rate Na we generally write as something like ky y minus yi, especially if it is a dilute mixture, but this is not a dilute mixture. Okay, it is a concentrated mixture. So for concentrated mixture we have to use the f type mass transfer coefficient Fg times ln of 1 minus yi by 1 minus y. Again you have to refer back to the lectures on interface mass transfer and mass transfer coefficient lecture, where I have shown expression for dilute mixture and concentrated mixtures. So now we are going to use this particular expression for Na. So these are the kind of differences or changes when we deal with the concentrated mixture in comparison with the dilute mixture. In the dilute mixture we used this expression, and the concentrated mixture we are going to use this. So now we can separate the variables. Is it right? So then, so as you can see that we are kind of dealing with very kind of clumsy set of terms here. Okay, there's 1 minus y and there's a logarithmic 1 minus y by 1 minus y and etc. So what we can do is just to kind of write this expression simply or in a shorter, in a brief terms, we can actually refer to what we know as this log mean difference. Okay, log mean concentration difference. You can see this term ln of 1 minus y by 1 minus y, and suppose if I write this as 1 minus yi minus 1 minus y over ln of 1 minus yi by 1 minus y. So this is something I can define as the logarithmic mean of the 1 minus y. Okay, this is the definition of the logarithmic mean. Okay, you might be aware that we have written something like delta y lm df is something like delta y1 minus delta y2 by ln of delta y1 by delta y2 in one of the classes, right? We use this for temperature difference in heat transfer. We also shown this for one of the mass transfer problem also. So now you can see that this expression is kind of very general. We can choose different driving force here. So here it is 1 minus y1 minus 1 minus y by ln of this term can be written as the logarithmic mean difference of 1 minus y. I am using this Im here because that is what is used in the textbook. So I am going to retain that instead of using LMDF. Okay, so this I minus Im here means it is the logarithmic mean difference defined like this. Okay, so once I define this, I can replace this particular term in terms of the logarithmic mean difference, right? So let's see. Now you can see on the denominator, I have y minus yi, and here I have ln of 1 minus yi by 1 minus y, and this is what I am going to call as 1 minus y, the log mean difference. So from here I can show the ln of this is 1 minus y Im over 1 y minus yi, and this term can be now substituted here. Okay. So on the left hand side we have z, and then we have integral minus y1 to y2 g by fga. Yeah, I still have minus sign. Which point you are talking about? Here, this way, just below. Okay, so here you are saying y minus yi, next line. Okay, so this comes, so yeah, good, thanks. So we are going to write this as y minus yi by 1 minus y Im. Is it right? Yeah, okay, thanks. Okay, so so we'll go back here. G by fga dy 1 minus y minus yi. So now I can change, so absorb the minus sign in the integral. So I can do this from y2 to y1, g by fga 1 minus y, sorry, so now we can define this term htg as g by fga. So z becomes integral y2 by y1 htg times 1 minus So, if you look at this HTG, this involves G and it also involves FG. I already said G can change along the column, okay, and so is the mass transfer coefficient FG can also be. So, if you look at G alone, it might change, but experience shows that if you look at the group of term G by F, okay, G by FG, that group term can be actually treated as a constant, because the variation in G and variation in FG kind of counteracts such a way that the group of this term is pretty much constant. So, I can pull out this entire term HDG outside the integral. So, it is not exactly equal, but can be approximated to this. So, we say that G varies and FG also varies, but G by FG term, this almost is constant. So, that is why we are pulled out of this integral. It is so mathematically it is not possible to prove, because the way that FG mass transfer coefficient changes with respect to the composition is a very there is no theory for that. For a given composition you can do it, but then across the column the composition is changing. So, it is purely empirical, that you look at possible changes in the y values and then you find this term, it seems to be almost constant. So, you do not have to factor that in, and it also allows us to separate this into two parts like HTU and NTU idea, like the way it happened in the dilute mixture. And then this entire integral we are going to call as number of transfer units. So, NTG is the number of transfer units. You have to remember this is not overall, okay, not overall. This is only with respect to gas phase number of transfer units. This is not overall. In the case of dilute mixture, we define NTOG, OG referring to the overall gas phase. So, here it is with respect to only the local local mass transfer coefficient. So, and similarly HTG, this also is defined without a O, it is only HTG, it is not overall, it is local. So, HTG is local, NTG is local, and these are the respective definitions, okay. So, we will box this. So, this is the definition of NTG, and HTG is the ratio of G by FGA. This is a height transfer unit. This is also not overall, it is local. Again, the calculation of HTG is very easy. You can find the gas phase molar flow rate, we know the FG, we know A, we can calculate HTG, but calculating of NTG is a little bit complicated. As you can see, it involves the interfacial concentration, and the interfacial concentration can be obtained based on the local mass transfer coefficient FL and FG, okay. So, from here onwards, either you can use this particular expression and deal with this complexity, or we can make some approximation and show this in a little bit more briefer form, okay, in a little bit in a simpler form. For that, what I am going to do is this logarithmic mean difference that I have defined before, I am going to replace that with an arithmetic difference. If I do that, if I make that approximation, then this expression can be simplified little bit more, okay. So, that again is an approximation, you can deal with it, this is more exact here, okay. If you know how to get the interfacial concentration yi for each of the y value, you can do this integral numerically, no problem. Okay, this is exact. But this expression looks very different from the dilute mixture. So if you want to kind of cast this formula in an equivalent form to the dilute mixture case, then you have to make this approximation that the logarithmic mean difference is now replaced with an arithmetic difference. Okay. So with that assumption, I can simplify this expression. So we have this. So assumption that we are making here, replace the logarithmic log mean difference, concentration difference, with arithmetic mean. Okay, so that is this 1 minus y I, sorry, 1 minus y I m, this was defined as here. Okay, this is our definition, 1 minus y I minus 1 minus y over ln of 1 minus y I by 1 minus 1. Okay, this is the definition. This is something we are going to approximate this to 1 minus y I by 2 plus 1 minus y I by 2. This is the arithmetic mean. So that basically will depend on how the operating line and equilibrium line are curved. If they are kind of straight lines, so this approximation is good enough. But if they become very curved and somewhere the concentration difference is very small, in some other places it's very large, and then come, so if it's a very variable driving force, which happens if the curvature of the two equilibrium line and the operating line are very different. Okay, so pictorially if I have to show, suppose if you have the equilibrium line like this and operating line like this, so all the driving force lines are pretty much similar. So replacing the logarithmic mean difference with the arithmetic mean difference is not a bad idea. But sometimes if you have a situation where you have a kind of very different kind of a curvature for the equilibrium line and operating line, then this driving force are quite changing, okay, across the column. So this approximation may be not so good. Okay, so like I said, this approximation is not necessary we should do. Okay, we can still deal with this. You are talking about the kind of problem in exams and that kind of, see, if you say in general, this is the most exact expression, you don't have to go anything further from here. But like I was saying, I wanted to, in the beginning of the class I said, right, that I know that for the dilute case, so for the dilute case I have a very nice separation of the terms, right, one that deals with HTOG and another one that is a simple integral of 1 over y minus y star. So I am trying to kind of write this concentrated mixture also in a similar form. Okay, so that's what you will see. The approximation I am going ahead is to get this in this form, where you have a similar form like this, except that instead of the equilibrium concentration, I will need the interfacial concentration, and then there is an additional term. Okay, so I am trying to write the general expression in this way by making one assumption, but that assumption is not a very necessary assumption. Okay, you can still deal with the original expression. Okay, this is only a kind of convenience just to show the form of the equations are similar for the dilute and the concentrated with some extra terms. Okay, so one can actually deal with this. This is not, it's going to be a little bit more kind of involved. Okay, but you can still deal with it. It is not like it's insoluble. The problem is still solvable. Okay, you can still solve it. It's just that it is in a slightly different difficult form. Okay, so we'll make this assumption. And then we go back to this NTG so this term 1 minus y I m, that's a logarithmic difference, that will be now replaced with this arithmetic difference, and the remaining terms are there. So now this can be split into two terms. Right. So you can see that I am writing this into two terms. So you can see that this is already in a desired form, that is the integral of the driving force, that is 1 by 1 minus yi, except that there is a factor of 1 by 2 that we have to deal, and then this particular term is still we have to manage. Okay, the integral of 1 minus yi by is an extra term. Okay, so now what I am going to do, am I missing something? Yeah, I think I am missing one term here, right? Yeah, so there is another term y minus yi. Yeah. So now I can write this. So looking at this particular integral, so you can do partial fraction of this, and then I will just show the final result, but you can check. So you should get something like, so if you separate this term with the partial fraction, you can show that this entire term can be written as sum of the two terms, and now I can do this integral easily. Okay, I am just talking about the integral of only this term, and this term remains so. And so here this term can be easily solved. You will get minus of ln of 1 minus y in the limit y1 to y2, and then you will have this term as such. So this entire term is for this. So now let me substitute this here. So I will have ntg is equal to 1 by 2 ln of 1 minus y2 minus by 1 by minus 1 plus 1 by 2 y2 to y1 dy by 1 y minus yi plus this term. So you can see that these two terms are actually the same thing. So we can just add this up. So you'll have this plus this additional term. So this is what I was hoping to derive, that the first term involves the integral of the driving force, and then you have an additional term that is constant, okay, because this just depends only on the y1 and y2 values, the inlet compositions. Yeah, so if you can see that this entire term I was telling the beginning, that's what we have derived now. So so you can stop here, or else what we can also do is sometimes we try to write this in terms of so if you look at this y minus yi, so what is this y minus yi? What is y minus yi here? This is a driving force, which means the composition at the operating line and then one at the equilibrium line. Okay, This is not the overall driving force, this is the driving force existing only in the gas phase, y minus yi. So sometimes this y minus yi can be very small, especially if the operating line and the equilibrium line are very close to each other, okay. And this integral will diverge because it will have very small values and very high values, and numerical integration of this becomes very difficult. So one way to manage this is to introduce this in a logarithmic scale, okay. This is not something very new, we do that. If you remember in chemical engine thermodynamics, we deal with the chemical potential equality, and then we say that the way in which a chemical potential changes with the composition is very drastic. So we write something called fugacity, where the fugacity is written as some logarithmic term of composition, okay, so that you can avoid this small values tending to 0, especially when you deal with this kind of integrals. So we can replace this particular integral in terms of logarithmic term, especially this particular term. This is not a problem because we can, this is a constant term, but this integral involves very small driving force at some point of time. So we will like to rewrite this in terms of logarithmic terms, okay. So for example, what I can do, I can write dy as y by y dy, right. I am just multiplying and dividing by y both sides, and then I can combine these two groups as y times d ln y, right. So then I can replace dy with respect to d ln y. So I will have ntg as integral y d of ln y, and here I have y minus yi, and the limit is also now changed to ln of y2 and ln of y1 plus the other term. And if you want to write in terms of, this is a ln with respect to base e, but if you want to do logarithmic with respect to base 10, you can also write that. So these are some other choices that we have. Either you can use logarithmic terms with base 10, or you can use ln, natural ln with base e, okay. So these are the two options we have. So in some of the numerical example I will use this particular formula. Okay, so just to kind of catch up and summarize, I want to kind of again re-emphasize that importance of this integral here. So we have y and x. Again, I am using mole fractions, not mole ratios here, and I have my equilibrium line, not necessarily a straight line, and then I have my operating line, also not necessarily a straight line because this is in mole fraction units. In mole ratio units only it becomes straight line, okay. So now you can see both are curved, and so this would be your exit compositions, and this would be your entry compositions. So what this integral means here is you choose different values of y here, okay. Let us say you take different values of y, corresponding to that y value you have to derive an equation for the driving force line, okay. So driving force line, and the driving force line is given by So the way I have obtained this driving force line is by equating the mass transfer rate from the liquid side and the gas side using the respective mass transfer coefficient FL and FG. Okay. If I use K type mass transfer coefficient, this will be a straight line. Okay. The driving force line will be a straight line with a slope of minus Kx by Ky. We have seen that before. But if I do this in a local mass transfer coefficient, F type coefficient for concentrated mixture, this need not be a straight line, it will be a curve. Okay, it kind of gives you a relationship between x and yi depending upon the ratios of the mass transfer coefficient. Okay, so we have to know this two mass transfer coefficients FL and FG, and then this YG and XL are the points along the operating line. Okay, and this particular equation will be the line coming like this. I am just drawing roughly. This would be not a straight line, this would be also a curve. Okay, so this is what will give you the corresponding yi. For each of the y, there will be yi here. For this y, this will be yi, and this equation is coming from the driving force line. So to get this integral, what you need to do, first you have to know what is the equilibrium line, you have to know what is the operating line. In the operating line, you choose a range of y values. For those y values, you have to get the corresponding interfacial concentration yi value from this driving force line. Once you have that, then you have to do this integral by plotting y by y minus yi, okay, and then integrate between log y2 to y1. So that's going to be numerical calculations. So I will demonstrate this in one of the class. Okay, such kind of problems can never be asked in exam. Forget about the gate. Okay, but this is only to understand know-hows. Given if you are a chemical engineer, if you want to be a chemical engineer, and this is something only you can do, no one else can do it. Okay, and you better know how to do it. Not in the context of exams, but in the context of pure learning. Okay. All right. Okay. So that's all. I'll stop here, and next class we'll do a problem.